Good morning, everyone. Morning, Tom. Morning, everyone. So my name is Matt Rocklin. I'll be talking about Dask. I've given many talks about Dask previously, and I'm actually going to assume that you've seen one of them. So I usually give sort of a generic talk, and I just have sort of an extra 5 or 10 minutes at the end to do something extra cool and fun. This talk is going to be all cool and fun things. That may not be what you're expecting. If so, there are a couple of resources you could go to. There's a PyCon 2017 talk this year, which is a pretty good overview. Jim Chris and Martin Durant also did a great Dask tutorial earlier today. The videos are already up on YouTube. So if you want to step outside, watch a YouTube video, that'll be just fine too. Today we're going to talk about a couple of things. First, I'm going to try to motivate you to try out some of the new task schedulers we've been using. So Dask had a task scheduler that we announced a couple years ago that was good for single machine parallel programming. And we've expanded that out to distributed computing. But that's also quite useful on a single machine too. So we're going to start to see some new features that allows, even just on your laptop. We're talking about some more advanced asynchronous task scheduling features that Dask has. And sort of towards the end, we're going to try to point people towards some development opportunities. So my goal is to get people to work on Dask, either on the code base itself, or hopefully within your own code bases. So Dask is really here as a service library for the other SciPy stack libraries. So we'd like to see it percolate out. Okay. But again, I'm not going to explain Dask at a high level. I'm going to assume that you have some exposure to Dask. Okay. Actually, briefly, who here has heard of Dask? That was really different 2 years ago. That's awesome. Who here has used Dask at least once? Okay, that's also really awesome. Who here has used a distributed scheduler? Oh, that's more than I was expecting. Hopefully we get more hands, though, at the end of the talk. Okay. So, that screen has a little bit of scattering. That one's darker. Okay, so the Dask distributed scheduler has a centralized scheduler which coordinates many workers. These workers could be on different machines. They can also be in the same machine. They could even be in the same process or the same thread. So even though we call it the distributed scheduler, it can be used effectively, just in a single machine setting. I'm going to use it very briefly to try to motivate you guys to also use it. So, that one. How's that in the back? Looking for a thumbs up, thumbs down? Okay. Well, that's what we're getting. Okay. So, if I have a Dask array, I can compute some computation, like I can add it to its transpose. This is a communication-heavy computation. Compute the axis of the sum. And that happens in around a second. Have it in parallel. We all like those things. So, you could also import the client object from the Dask distributed library. And now usually when we make a client, we point to the address of some distributed cluster somewhere. If we don't do that, it'll create for us these workers and schedulers in our own machine. So if you just call client with no arguments, it'll set up everything up for you. Then all of your computations will automatically use that scheduler by default. In this case, it's actually going to be slower. I've intentionally chosen this example. It's a bit slower. Adding an array to its transpose is communication heavy, and here we're actually communicating a lot between different processes. When we're using the threaded scheduler, we didn't have that extra cost. So why would you use this? One reason why is because you have all these flashy diagnostics. This is a bokeh server application. It's a streaming application that I'm shoving diagnostic information into on the Python side, and it's showing up on JavaScript. So I'm going to run that again. One of the nice things about the Dask distributed scheduler is that it exposes a lot more information about what's happening internally. Okay. So we can sort of zoom in a little bit here, and we can see, what every core, every row is one of my cores, what it was doing over time. This particular instant, it was transferring some data. That transfer took around 500 milliseconds, and it was also creating some data at the same time. It was overlapping communication and computation. So diagnostics is one reason. The other reason is you have more new fun tools. For example, the distributed scheduler can maintain state. So previously, with the single machine scheduler, you would give it a graph, and it would compute that graph and give you back a result. And here we're saying, compute this thing and hold on to it for a while. I'm going to do other things with it in the future. So now if I do something like compute a sum, the random arrays have already been computed and they're sticking around. So we can compute things much more quickly. So there is some overhead to using the distributed scheduler, but you can generally be much more intelligent with it. So you get diagnostics, you get new features. We'll talk about those features throughout the rest of the talk. You can also scale out. I actually have or had a terabyte cluster sitting around. It was right here. Unfortunately, I think Continuum has gotten a lot better about cleaning up $100 per hour clusters when I leave them idle. So I'm starting up one on this laptop, and maybe by the end of the talk, it'll be running. But in the meantime, it'll make me a little less pressured for time, which is nice. The Dask distributed scheduler is also very lightweight. So it doesn't need to run many processes. You can run the same process. It doesn't have to use sockets. It can transfer data around just with queues. And so here's an example where we are starting a new cluster. We're connecting to that cluster with a client. We're submitting a new task to that cluster. We're receiving the result back. We're then tearing down the cluster and closing the client. And that finishes in 38 milliseconds, 39 milliseconds. So you should think of the Dask distributed scheduler as being a very lightweight thing. It takes much longer to import pandas than it does to do all these things. So again, you should not, Dask is lightweight. We're now depending on Tornado. We're depending on Cloud Pickle. But that's all. So if you write a library, you might consider depending on it. This single machine scheduler is still more lightweight. It's just end-of-lib only. But if you add a couple more dependencies, you get some of these nice new features. By the way, in case the contrast here is a bit poor, I apologize. I've tweeted the slides with both the SciPy 2017 hashtag and the Dask hashtag. And you can look at all the examples there. It should be much more clear. Okay. Thanks to Antoine Petrou. I'm going to try to call out people who have done good things for the project recently. Antoine Petrou totally refactored the network comms and the setup and the process handling. So he's who's to thank for that 39 milliseconds and many other things. Okay, so I showed you an example where the Dask distributed scheduler was actually slower than the single machine scheduler. That's why I try to show the worst case. Here's a better example. So Ian Oswald tweeted out this picture showing Dask dataframe and how it's speeding up his pandas computations. So this line is taking around 19 seconds to run a computation. And with the Dask multiprocessing scheduler, he's able to get around a 2 or 3x speed up. And he's playing here with a number of partitions on the x-axis. But the best case gets sort of 2-ish x speed up. 12 hours later, I said, hey, this is really great. You want to try some different schedulers. For anything that's sort of pure Python-y, and he was doing some string processing, you want to try the Dask distributed scheduler. So immediately afterwards, Ian retweeted this plot, which shows the difference between the multiprocessing in green and the distributed in blue. I actually don't know what the computation is, but this might be representative of a typical computation. So lesson, if you're using Dask dataframe or Dask bag, if you're doing anything that's not definitely GIL-free, the Dask distributed scheduler is probably higher performance. It also gives you fancy plots. Array users may still want to stick with a threaded system, so you can start that with process equals false, or just continue using the original schedulers. You may also have a cluster, and many people doing array computations do. That community seems to usually have access to some academic cluster resources. Lesson number 2, if you tweet benchmarks, you can get really great priority support. I will write features and fix bugs for blog posts. So. Okay, so that was about Dask Array a little bit. I don't actually want to talk about collections anymore. I want to talk about new things. So let's talk about a motivating science example. Science. So this is my rendition of a synchrotron. It is a big circle in which X-rays fly around very fast. At various parts in that circle, those X-rays can a port can be opened up, and those X-rays can zoom out and hit things that we want them to hit. After they hit things, those photons tend to hit detectors. So if you look at one of those exit ports on that big synchrotron, it looks kind of like this. This is a photo credit to Dan Allen, who took this photograph at Brookhaven National Labs a couple days ago. He unfortunately couldn't come to SciPy. You'll notice the date up there. And this is clearly science, right? Here's some user interfaces that are definitely not web-based. Over here, we're going to zoom in, and here's a big spiky thing that's encrusted in aluminum foil. So you know that it's science. There's even some caution tape flying down here. Okay. And so, photons are zooming through, and notice also these 2 computers that are sitting here. So as those photons hit some detectors, they get counted, and we eventually get those counts as NumPy arrays, and it becomes our problem. Okay. And so now, those images are not the images that we actually want to see. We need lots of processing on them. That processing can be complex. Fortunately, we have scikit-image, and we have NumPy, and we can make lots of custom computations. Eventually, we want to store some of those results, both the raw images, some of the evaluated from the computed images, into a database. This isn't big data, so Dask is not necessarily just a library for big data computations. They're not big arrays, but there are lots of arrays. We're doing complex things with them in a real-time fashion. Additionally, we have scientists who are sitting there looking at their screen who would like to twiddle knobs, have that affect the computation, and have that affect their screen again. So this needs to be real-time and fairly fast. We're talking about some real-time applications here. To handle all this computation, we have some resources. One, we have 2 computers that are physically at the station. Notice these 2 screens. And they can do some work for us. However, as we sort of tweak some of those knobs and some of that we get more and more images, we might have to overflow to a nearby cluster, nearby data center. Okay, so we're going to build this pipeline system using Dask. And to be clear, Dask is not a system for building image pipelines. Dask is a system that you can wrap around your own problem. And that's really the intent that I want to convey here generally, using this as an example. But you might want to think about your own problem while we're going through this example. We're talking about the concurrent futures interface. This is a standard Python interface that we have implemented and extended. It tends to be a little bit better for real-time things. It'll be just as flexible as Dask delayed, if you're familiar with that, which again, I'm assuming that you are. We'll talk about changing computational graphs on the fly. We'll talk about some multi-client workloads. We'll see what that means. And we'll also talk about worker coordination primitives, like queues and globally shared variables. Okay, so the concurrent futures interface. So we're going to make a client. Let's see if I can get that a little bit bigger. Reveal's not doing this thing. We're going to make a client, and then we can submit a task to run on that cluster somewhere. Here, the cluster is just our laptop. And we do that by submitting the function and then a sequence of arguments and keyword arguments. That gives us back immediately a future, which is a pointer to computation that will eventually be done, and a pointer to that address. Whenever it finishes, it'll point to that address in distributed memory somewhere. That computation happens in the background, and in the background, we learn about its status. So we just wait for a little while and print that future again. We'll learn that it is finished, the type is int, et cetera. If we want to, we can then gather that result back. So result will block on the computation and gather a result back to us. However, we usually don't want to gather results back to you. By default, they stay on the worker where they were computed. And so here, you might want to submit more tasks on those computations. In Dask distributed, with the concurrent future interface, if you submit a task on top of other futures, it will cause a dependency, like here. This is very, very similar to how Dask delayed works, except that now we can control it on the fly. It's real time. So as these tasks are happening, we can watch what's going on, we can update them, we can cancel them, we can add more tasks based on maybe good areas. So again, as these features are happening, we're getting back status updates. The first feature here is still running, is still pending. The second feature is finished. And we can, based on these status updates, we can do whatever we want. We're in Python. We can collect all the bad ones and see what the exceptions were, find all the good ones, gather the results, submit more tasks that are maybe around good results. As an example of that, so there's AsCompleted, which is also part of the standard concurrent futures interface. We try very hard to follow the standards where they exist, and then sometimes extend them. So AsCompleted gives you, we're going to use some of these things. So I'm going to go through a list of features. I apologize for speaking quickly. So as completed, you give it a bunch of features that are running, and it gives you those features as they complete. So it may be that your first feature doesn't finish first. Maybe your fifth feature finishes. Make them out of order. In this example, we are gathering these features, and as they come in, we're trying to find the best one. And maybe if we find the best one, we say, hey, well, this is good enough. I'm just going to cancel out of here and cancel the rest of my work. I found something nice enough. This is a good example where being able to operate on the fly can give you some efficiency. This is a very simple example. You might think of other ones. Another fun example here is maybe, again, I've submitted all these features. I'm getting results back as they come. Whenever I find a particularly good result, I want to submit a couple of other tasks right around that result. Maybe I'm searching. So in this way, I can sort of guide my computation as I get partial results. And again, you can think about some optimization, machine learning algorithms that sort of look like this. As an example, let's go and look at, this is from Jim Christ. So I'm going to try to optimize this function. This is the Rosenbach function. So I'm going to connect to a client. Oh no, I don't have a cluster set up. I need to set up some schedulers and workers because I wasn't cool enough to not include this address. But it's okay. I can start a command line terminal from within my Jupyter Lab experience. Isn't Jupyter Lab the coolest? started a scheduler. As that scheduler pops up, you'll see the client connects. Let's make a new terminal as well for a worker. The Jupyter Lab guys are buying me a beer tonight, by the way. They don't know that yet, but they agree. So this is how you set up Dask on like a cluster experience. You might SSH into them. You might use this with some other cluster system. But that's, you start a scheduler, start many workers, and as those workers connect, we'll see that we've connected up to one worker with 4 cores and a few gigabytes of RAM. So I've got this function, which is in code here and visually here. I apologize for the poor color map. This is what's on Wikipedia. And I want to find the minimum value of that function. So what I'm going to do, is this anywhere near visible in the back? Great, thank you. Okay, so I'm going to submit that function to run on many points, maybe like 10 points. And then as they come in, I'm going to get their score in the point. And if it's better than the best score that I've seen, I'm going to print out some results. So we'll sort of see some scores coming in, which will be pleasant to see. And then every time as a new point comes in, I'm going to submit a new candidate to test that's somewhere around the best point that I've seen so far. And as we continue, I'm going to sort of reduce the scale that we look at it. So we're going to sort of zoom in on the best point that we've seen. Okay. As I do that, I'm also going to want to show, actually I think I have this already up. I also want to see the diagnostic page. And that's concerning because that's the last diagnostic page from this client, which means I'm going to restart these. Everyone reconnect. Now the bouquet app is in place. Excellent. Okay, so let's go ahead and start that running. And what you'll see is that we're getting results as they come in. And we only have about 20 tasks running. If you look at this progress bar down here, we only have around 20 tasks running at a given point. But as tasks complete, we launch new tasks again around that good area. And so we're getting closer and closer. It seems like we're zooming in pretty far on this value of 1,1. Seems to be the optimum point of this function. So we wrote, a relatively naive, but we could have made some choices, relatively naive algorithm to do optimization and search. And we did it relatively easily. We did that with these primitives. So these are sort of nice things to use to build out some more complex algorithms. Okay, what's my time? Great, okay. Okay, so other feature we're going to need to submit tasks from other tasks. So we're going to run some function on some worker, and we're going to want that worker to itself submit more tasks to run other workers. How we handle this in Dask, so usually you have a single centralized scheduler, you have many workers, you have a single client which controls that scheduler. You can actually work with your friends on the same cluster. This is really helpful if you have maybe like a terabyte data set you're all working on, you want to share that data set, maybe share results back and forth. We're not going to talk about that today, but that's also possible. What we are going to talk about is you can have all of those workers themselves start clients that can then control the rest of the cluster. So this is like if you're flying a plane, you gave every passenger like the controls. But it works out pretty well. We need to coordinate, but it works out pretty well. How that looks like in code, there's a few functions we're going to care about. Inside of a task, you can call these functions. Get client, which means give me a new client that I can use to connect back to my scheduler. Get worker, I want to affect the data locally on my own machine. Succeed and fire forget, you should look at docs, we won't get into them. And so we can submit a task, this function, that itself gets a client and then submits more tasks. This is cheap to do, it's fine, there's no sort of performance penalty here. And this small API change allows some very complex workloads. So here's the Fibonacci, here's computing Fibonacci, and this runs fine. Okay. There's also things like MultiClient Coordination. Dask has things like distributed queues and distributed global variables that clients can use to coordinate metadata. You can create futures. I'm going to move on a little bit. So here's an example of a MultiProducer, multi-consumer system built with Dask with this interface. This is a classic kind of parallel programming system you might want to build for data processing. And here we've built it in around 15 or 20 lines of code, using systems that Python programmers already tend to know. People tend to have worked with queues before. They've worked with concurrent futures. It's using APIs that are relatively familiar, but again, scaling out to that cluster. OK, so let's think about this Beamline example. So if you are looking at the slides, there's a gist of the code that's been handed to us. So we have been handed some loving code by some of our scientific colleagues that has a function to return to us some data from a detector. The detector is counting photons. And for us, we're just going to simulate this by creating a random array. But once we sort of have a synchrotron, we might use that. We have some silly small functions, which are going to simulate some work. And we also have this function which is going to save that data to a database somewhere. This is just doing a side effect. It's not really returning anything for us. And you have this loving message from our collaborators asking us to please compute this sort of computation on each of our arrays and save it to a database. I am low-ish on time, so I'm just going to switch to the solution, which looks a bit like this. So while we're looking at that, I'm going to set up our Beamline system. So on some machine, I'm going to have a scheduler. So this isn't running on a laptop, right? We're actually running on different machines. So we're going to simulate setting up a cluster in that setting. On one of the, that's right, I have another scheduler running over here. On one of our Beamline machines, we're going to connect up to that. We're going to connect up to that scheduler. And we're going to give that a name. This is going to be machine Beam1. So Dask has the ability to localize computations to certain machines or machines with certain resources like GPUs or big memory. There's another one. And then we're also going to make just sort of a pool of workers somewhere else. This is on our, we'll make maybe 5 of these. This is again on my laptop, but this is actually on a data center somewhere in theory. So great, we've got all those machines. Our sort of Beamline is set up. And what we're going to do is we're going to keep in a while loop calling get data from image from detector. We're sort of send it out to the cluster. We're actually on the cluster, so it's going to be a free operation. We're going to submit some tasks. That's the computations our users want. We're then going to submit these sort of saving operations. We actually don't care about those results. We want them to definitely happen sometime. So we're going to call this fire and forget method function. I'm not going to get into it, but there's good documentation on that. Then we're going to connect up to our cluster. We're going to set sort of a sleep time. So we want to wait 2 seconds between detection intervals. Then we're going to target this function. This function is going to handle each beam to each of our individual workers. So we are submitting the collect from beam function to Beam1 and to Beam2. So Dask is usually, it just sort of runs functions wherever is best. We can also direct it. I want this thing to run on this machine or on these kinds of machines. And that can be very useful in certain situations. So let's go ahead and run this. Let's get the right space. Okay, we see we've started these 2 tasks here, collect from beam. There's 2 of them. And they're never really going to finish. There's always going to be running. You see that every couple of seconds, a bunch of tasks start showing up on my workstation. So this is our beam firing off some tasks, and things start running. Now we have this knob, this sleep time knob, which we can set. So it's currently set at 2. And we can now set it, let's crank things up a little bit. And instead of getting an image every 2 seconds, let's get an image every 100 milliseconds. So what this is going to do is now those tasks are now firing off NumPy arrays way, way faster. And as you see, they start to saturate. But that's OK. Our other workers have sort of kicked in, and they're starting to handle some of that excess. So that's an example of using Dask in a non-trivial example. This is almost certainly not what you guys do. But Dask can be used in lots of interesting situations. So to wrap up, you should try out the Dask distributed scheduler. Has a variety of good features. We've seen a particular set of features around real-time operation, but there's many more that you probably haven't seen. Now would be a good time to look at documentation again. Some things people should work on. So there's a lot of good projects to work on. These are not easy projects. These are hard, but they're the kind of thing that might generate a talk in the future. So I'm being kicked off the stage soon.
So if we could thank Matt for that talk. If Sam could come up and start, Sam Penrose could come up and start getting the computer set up while Matt takes some questions on the side.
If you have questions, I think there are microphones there.
Or wave your hand and I'll bring you one.
Or wave your hand wildly.
What are some projects I can work on?
You work for Continuum with me.
What are some projects that people in the community can help out with?
There are tons of projects. First, you can use your own projects. We're doing a sprint tomorrow and the next day. This is not about contributing to Dask. It's about using Dask within your own code base. If you don't have anything, there's some nice things. We're working on some GeoPandas stuff, some streaming data frames. But ideally, we'd love to see you show up with your own problems that you want to use Dask for.
Hi, over here. I love that dashboard, by the way. Is that just does it automatically get instantiated when you bring up the workers, or how does it work, or what do you need to set up for it?
So that is a bokeh server application, which is a fantastic project. I really enjoy it. It's about 800 lines of Python code to get that running.
Okay.
For us to build it, rather. When you start up a Dask scheduler, it runs automatically. There's also another one running on all the individual workers. So it's just running automatically for you.
Oh, awesome.
Yeah.
Thank you.
Are there any other questions? All right, let's thank Matt again.